So we are doing, let me show the screen. We are doing a synchronous generator lab. And if you think about what a synchronous generator, the purpose of a synchronous generator is to convert, right? Not to create, but to convert mechanical power to electric power, right? That's kind of the important part of it. And how it does it is you have to have a magnetic field, part one. You have to have a magnetic field that is changing, rotating in a closed loop, part two. And sort of sneaky in there is that rotating inside that loop, or rotating in a loop means you have to have some sort of device that is going to drive that current carrying, or not current carrying, but that magnetic field that's going to cause it to rotate. So in a synchronous machine, what we realize is that we got to have a fixed magnetic field on the rotating part. Okay, there are some exceptions where the fixed DC field is on the stationary part, but those are pretty rare. They do exist, but if anybody wants to know where you find them, please seek me out. But for the most part, we'll assume that the rotating part is going to be on the DC is going to be on the rotating part. And so because of that, the rotating part is just rotating the magnetic field, which means you have to physically have something that's going to rotate it. And so in the case of a synchronous generator, you have a mechanical system that is rotating that magnetic field. And the rotating part of it comes from whatever you want it to be. It could be from a steam turbine. It could be from a gas turbine. It could be a hydroelectric dam. Those are the big ones. Nuclear power plant. Does anybody know what would be how a nuclear power plant would provide the mechanical force?
Steam.
Steam, yeah. So even though I talked about a steam turbine, I was being sneaky there because a steam turbine is any place you can get heat to create steam is going to use that steam turbine. So it doesn't need to be a boiler-fired plant that might burn coal or trash or whatever. Could be nuclear, right? Nuclear is not burning anything. It's certainly heating up the water, but you get the idea. So steam turbine, gas turbine, hydroelectric facility, right, which is actually water pushing on it. I mean, if you wanted to push your fitness, you could certainly take your bike and connect a synchronous generator to it and go ahead and start pedaling away and see how many watts you can produce. It is kind of interesting. There's a video, it's getting kind of old now, maybe from the past 5 years or so, but there's like this world-class German track cyclist, and his job is to toast a piece of bread. So this person who gets in there is just a monster. I mean, he's just all muscle. And I don't know how long he pedals for. Not very long, maybe an hour, maybe a minute, I should say. And just to toast that piece of bread, he's dripping sweat. So if you look at this guy, you're like, man, this is the fittest person in the world. But that just shows you how much energy is in fuel, for example, gasoline or whatever. So I've started to go ahead and build this system here because why? I need a source of mechanical energy. And the mechanical energy is going to come from this 4-quadrant dynamometer. So you should be able to drag one over and put it in your LVSIM window. You will notice that I have it directly adjacent to my synchronous motor generator. Why is that? Well, because this is a mechanical system. I can't just run wires through the air and make this work. I have to mechanically couple those two together. So if I right click and I lower the front panel, you can actually see a motor with a shaft that's connected to a pulley system, right? And if I do the same thing over here, I can see, and you can see they just took a picture of it. They do look different if you're in the lab, but essentially you have the shaft of in this case, the prime mover with, some device to go ahead and couple to. Then anybody know what these things are right here? These two, can you see my cursor moving around?
A little on the small side there, but I'm
Better.
Yeah, let me make the I mean they look like bearings.
You can see bearings inside there. Yep.
Yeah.
So what would these be?
It looks like a belt tensioner to me.
That's exactly right.
Okay.
It's a belt tensioner because if you just ran a belt from here to here, the only way to keep tension on the belt would be you'd have to eventually go ahead and kind of relocate and pull these motors further apart to make tension. This, you can see the spring, that's actually going to allow it to maintain tension. So if you click here and you drag over here, you'll actually see what would look like the belt between the belt tensioner. And you might think this is silly, but this is exactly how we do it in lab. We just have to, it's not dragging the mouse, we have to physically connect it. So
Is that, I'm sorry, I hate to interrupt. Is that the prime mover dynamometer or is that the 4-quadrant?
4-quadrant prime mover dynamometer.
Okay.
And then next to it is a synchronous generator or synchronous motor generator.
Ah.
So once I have these two coupled together, I can raise the front panel here and raise the front panel here. Okay. So this is, I think, like the only time that I can think of that you actually don't have to connect power to this module to get it to work, but you can actually see power input. You can see this is an AC input. I can flip that on and I can get that to go ahead and start to display information. Now, if I want to go ahead and actually get some information, this is the actual control for the 4-quadrant dynamometer. And I'm going to run that as a either clockwise or counterclockwise, it doesn't matter. But I'm going to go ahead and change the speed. So let me change it to 1800 RPM. And then go ahead and start it. Okay. Look it down. And kind of hard to see, but it actually is rotating. It tells you it's at 16, 40, 51, 52. I want it to be 1800 RPM, but the way these things work, this is trying to monitor the speed. And then there's a characteristic in here called the droop characteristic that is kind of making it go a little bit slower. So I'm just going to manually rotate the knob and get my speed to change. It's not changing there, so I might have to change it over here. Let's change the knob over here. And I'm just going to increase it. It lets me grab it. And you can see it's going up and up and up until I get to around 1800, give or take RPM. Okay. Now, this is really, go ahead.
Sorry. How did you open up that menu? I was grabbing my printout of the lab.
Oh, I was going to ask the same thing.
We'll show
Okay.
you. This menu right here,
Yeah.
Yes. Where did you get that?
if you hover over this icon,
Ah,
that gives you that.
Which icon?
It's right here. You can see it's up here.
okay, because mine's grayed out. It won't. Weird.
Where's is grayed out?
Yep.
Anybody else's grayed out?
I got mine up. I think you might have to turn it on.
Okay.
Yeah, did you put the power input on, Rita?
Oh, you're right. That does help. I have it now.
Thanks, Andrew. All right, so now if we start and stop this, so I'm gonna have to start and stop it from here. We'll actually see. Gets up to speed, and then you can see both of these are rotating. And it's not 100% rotating at 1800 RPM. Again, it's just a bunch of pictures. But if you were in the lab, you would actually hear it spinning up and getting faster and faster and faster until you get whatever speed. Okay. So that's the first part of actually being able to use this lab is providing the mechanical force. The only reason why we need this piece of equipment is to be able to drive that. In lab, we don't have any of these. They're quite expensive. So we did a slightly different setup to make it work, but we could get it to work here in this lab environment. All right, I'm going to go ahead and stop that because this is all well and good. But my question for you all is, if this thing is spinning at 1800 RPM, I know it says 1959, but if it's spinning at 1800 RPM, does it actually mean that this synchronous generator is going to put out a voltage on these phases here? What do you think?
No, you have to excite the.
Yeah, I need a magnetic field, don't I?
Yep.
And right now, this is just a hunk of iron that's spinning around. So the way that I can get a magnetic field is I'm going to go ahead and run DC into the field winding as shown here. So this is just plus minus, and it's going to be 120 volt DC, not AC. So remember, it needs to be a constant magnitude and not alternating So we need to run positive DC there. And you can actually follow along. This is an on-off switch just to indicate is the field on or off. This goes and you can actually see some of the commutator and brushes here, provided in north and south. And then just to make things easier, they have this rheostat in here that allows you to adjust the current. Because when we have the field current, because when we have a fixed 120 volt DC, it's difficult for us to go ahead and control the current. So we add this rheostat in here to go ahead and make that work. Okay. So now I'm going to go ahead and monitor the voltages. So I'm going to go ahead and set up my oscilloscope. But I'm not going to be able to view anything yet because I haven't set up my data acquisition, have I?
Nope.
So let's go ahead and set up my data acquisition. I'll monitor phase 1. That one. Phase 2 with this one. And it doesn't matter if you monitor 4, 5, 6, or 1, 2, 3. It's not going to change your results really. I mean, you might get a positive instead of a negative, but 180-degree phase shift essentially. That's it. All right, so I'm ready to go ahead and start this thing up, correct? I'm monitoring the 4 voltages, or the 3 voltages, so am I good to go?
No.
What am I missing?
What you're missing the return path.
Yeah, these have to be connected to come back.
Yep.
Now, can I connect 1 to E1 over here, 2 to E2, and 3 to E3?
I mean, I suppose I don't know why you'd want to. I would probably, you want to monitor each phase independently, don't you?
That's a good question. Do I want to monitor each phase independently?
I think so.
Well, I would kind of challenge your phrasing on that. I don't want to monitor these independently. Why? Because this is a 3-phase machine. These 3 windings are physically separated from each other in the machine, and there's no electrical connection. So I'd like to make this a Y or delta configuration so I can actually get a 3-phase supply. Because if I measure the voltage from 4 to 1 and compared it to 2 to 5, I'd see a difference there, but I wouldn't be able to get any power flow through there because there's no return path. Remember, the electrons that go out terminal 4 have to come back into terminal 1. So if
Right.
I don't have any internal connection to 1 from 2 or 3, it ain't going to work.
All right, so you can just tie all those together, put one over to E1 and then tie the other one together.
Arthur's correct, except what is the minor nit issue that Arthur has proposed? This is a really subtle one. What type of connection did Arthur build me? You only have 2 connections, right? So what did you build me?
I would think a Y.
You built me a Y connection. What if I actually wanted a delta?
Oh, well, that complicates things a little bit.
Right. And I'm not saying we need to make this Y or delta. You can pick whatever you want. I'm just saying if you wanted a delta connected machine because you wanted your line voltage and your phase voltage to be the same, this ain't going to work. But we'll make it a Y to make it easy. And Arthur's absolutely right. Let's drop over here on any phase because they're all shorted together. And move that out of the way just a bit and connect this to this. Move that out of the way. And this to this. Oops, I'm going to connect. Guess I have to delete it. Okay, so now I'm going to go back to my metering in here, and I'm going to see if E1, E2, and E3 are set up to monitor voltage, which they are, and they're monitoring AC voltage. So if I flip the switch, everybody think that they're going to get power now?
No.
No. Well, first thing is I didn't actually energize the DAC, right? So I got to run this over here. Flip that switch.
You're still not going to get juice.
Well, let's see if I can stop it. That's over here.
That's okay, but you ain't going to get none.
Well, it's speeding up.
So,
Yeah, this is a problem. You should be running DC across here to get it actually operating as a motor load, essentially. So this one is a little bit goofy in how I've got it set up. It's not perfect, but it does the idea. So now let's go back to our metering window for our oscilloscope, and let's actually turn on are channels. And I don't want channel 1 to be anything, right? Because I want them all to be Y channels. This is going to be E1. And this is going to be E2. And this is going to be E3. Turn this on to continuous refresh. All right, so what's happening? No voltage, right?
Yeah, you didn't excite the field.
Yeah, just because I turn this on, I still have to flip the switch, right?
Yeah,
Because it's open.
not unless there's like a permanent magnet in there, but
There isn't. There is not a permanent magnet, so I need to energize it.
yeah.
So
Yeah,
I flip the switch.
that little knobby knob there.
There you go. Now I'm getting a voltage. And if you look closely at it, let me pause this. I'm getting pretty nice looking waveforms, right? So my question is this producing a balanced set of voltages? Remember the rules for balance, same magnitude across all three, and a phase shift by 120 degrees. Do I get 120 degrees of phase shift between the three?
Looks like it.
How can you verify that?
Well, the peaks appear to be equidistant.
Yep. So you're looking at it, but how do I do the math behind it?
Oh.
Everybody remember this?
Mm-hmm.
Using my cursors.
Yep.
I'm looking for the peak points here. Correct?
Yep.
So now I see a difference in the peak times. Yeah. Or you can do zeros. It doesn't matter. So I see that I don't know if that's purpley, is channel 3, and the red is channel 4. So how can I detect if that's going to be 120 degrees? Do you have enough information to do that?
Yeah, I'm sorry, I lost you there for a minute.
How do I calculate that I get 120 degrees?
Well, I see that you dropped the cursor.
I drop the cursors and it looks like I'm getting pretty close to 2 peaks.
Mhm.
If you want, I can zoom in a little bit more. And how do I do that? I will zoom in by doing my time. Oh, I can't change the time. I want to change it from 5 milliseconds. Oh, time base right over here. So if I want to display more zoomed in, which way do I go? Do I go to 2 milliseconds or I go to 10 milliseconds?
Who?
2, because each of these major divisions takes 2 milliseconds. Right now it takes 5. So if I zoom in, I go to 2 milliseconds. Or I go to half millisecond. Now you'll really see it zoomed in. Okay, that was too much. So let's go to 1. Because I want to see at least 1 peak. Actually, 1's not even going to work because this is bouncing around. So let me go to 2. Okay, so I'm going to pause this, and now I'm going to move my cursors, and now I'm going to actually do 0 crossings. Because if I use 0 crossings, I can look on my blue line here. I can look when I see my value is going to be equal to, 0. So I'm going back, and you can see it's minus 21, minus 18. And when that's perfectly or as close to being as 0 as possible, can't get there. Whoops. I think that's the best I can get. I'm going to do the same thing for this purple waveform. Get as close to what I can get to 0. It's either minus 1.27 or 2.4. So I'll go minus 1.27. All right, so now you're all whizzes. How do I calculate phase shift? How do I get 120 degrees? Is it on there?
It's going to be trying to remember the formula. Yes, you use the time. The time is the period.
Keep talking.
Oh, I'm trying to remember. It was like 360 over. Oh,
You're on the right track.
yeah. I'm trying to remember that. but yeah, it's the difference between the peak and time over the time and period times 360.
Anybody agree with him? Not sure. I'd like to bring up whiteboard if I can do it, but my computer's causing me some
Yeah.
difficulties here. It's like it's not allowing me to search. Where are all, let's try that. Guess I have to do it the old way.
Divisions 50.
Oh, whiteboard's not showing up on the list. Let's see if I can do a search.
Yeah, just kind of. Oh, where is that?
Not allowing me to show you. It's not bringing up whiteboard, interestingly enough. It's like it's blank. All right, well, I guess I'll just have to do it on a blank piece of paper because whiteboard wasn't cooperating. Let me share my screen on the other side. Okay, can you see the Word file? Oop. That's the one. So Arthur was on the right track, right? How long does it take to do one complete cycle?
One period.
T, correct? What's another time? Or another way to say one complete period?
1 over F.
That's the frequency, yeah. Any other thing?
Wavelength.
Yeah, but we're not, that's pretty fancy. How about plain old 360 degrees, right?
Oh,
True.
Right?
Right.
yeah.
Simple one. So 1 period equals 360 degrees, isn't it?
So that's true.
And Arthur gave us a hint. He said periods equal to 1 over the frequency. So 1 times 1 over F is equal to 360 degrees. If we're assuming 60 hertz, 1 over 60 hertz, which really has a units of seconds, right? Because 1 over F is equal to seconds, but F is equal to hertz, which is 1 over seconds, equals 360 degrees, right?
Yes.
So far, so good. So I'll get rid of this. So let's see. So 360 degrees multiplied by 60 over 1 times 1 over seconds gives me degrees per second, correct?
Mhm.
So 360 times 60 is the unit conversion to go from degrees to seconds or vice versa. So if I take my time, which is 5.49, and that's in milliseconds, and I multiply that by 360 times 60, what do you think I'm going to get?
5.49, you said?
5.49. I cannot do anything. It's like won't even launch MATLAB. I might have to reboot my computer because I'll just try calculator. I can't even do calculator. Huh. Oh, there it is. It just seems to be really slow.
118.59, 588.
118.58.
Yep.
So what is 118.58 really, really close to?
Really close to 120.
Very good.
So you're not at yeah, and that makes sense because you're not at exactly.
I'm not exactly at zero crossing. And there's also some resolution, right? I mean, I'm never going to be perfect. So let me go back to sharing my other screen.
Although the utility is perfect.
Well, they're much better than I am, that's for sure. But they have reasons to be. They get paid differently than I do. So, but yeah, you can go ahead and check the zero crossings, and you can see I have 120 here. If you did the same thing going from purple to red, you get 120 degrees. So the question on the table is, why is that? Why do I get 120 degrees of physical separation here?
that's built into the coil.
Say more.
The windings are mechanically 120 degrees apart.
Yeah, the windings are physically 120 degrees apart. And so when that magnetic field crosses through, it's going to get a peak, and then 120 degrees later, you're going to get another peak. And then another 120 degrees, you're going to get another peak. And those are phase shifts because you physically constructed the machine to have those windings to be 120 degrees apart. So, will I get any different results if I change the speed? Will my oscilloscope look the same? Will it look different? What do you think?
If you increase the speed, you'll increase the frequency.
Yeah. Anybody have any other thoughts or comments on that? If I increase the speed, and I'll do that on the side here. The frequency is going to change. How about the 120 degree phase shift?
Nope.
No, it doesn't change. It's still going to be the same. So I'm going to increase this to, let's say, about 2000 RPM.
Um,
You're crazy.
yeah.
I'm crazy. Why?
You trying to make that thing fly apart?
Well, it's all simulation land, and we're not connected to any load, so
True.
it's not going to hurt anything. But here is 1994, close enough, right? Now I'm going to go ahead and I'm going to make this so that I can get different data. And you can see it's much tighter, right?
Yeah.
So I'm going to pause it here to here. Oops. And I can go ahead and if I take the difference here, I can get it. But this one's a little bit harder because before when I said 1800 RPM, I was assuming 60 hertz. If the machine is running at 2000 RPM, the frequency is no longer going to be 60 hertz. How can you tell what the frequency is on this?
The time.
Yeah, it tells you right here, right? It says 66.48. But the other thing you can do is I crossed the zero going from up to down. So if I wanted to actually do that calculation by hand, I would go ahead and do that. And so you can calculate the time. It says it takes 14.99 milliseconds to go there. What's 1 over 14.99? It's about 66.848 hertz, right? And again, I'm not being perfect because this is real world and I don't have the exact devices to make it work. But that's how I end up with the data that I get there. Okay. There's one other way to measure this. Anybody want to guess? What would be the other way to be able to check to see if it's a balanced system?
Could we use the phaser plot?
Yeah, phasor analyzer, right? So if I go over here and click over here, this is even better. But this is a fancier device. Most of the time you don't get to see phasor analyzers in the real world. But over here, whoop, we get to. Let's toggle that on. And there you go. Magnitudes are the same. 120 degrees here, 120 degrees here, 120 degrees there. And I'm going to go ahead and adjust the speed. If I keep that up, so I'm going to go back to 1800 RPM. Watch what happens. See if you notice anything that happens. It's like the speed is not changing. It stopped. Hold on, just bear with me because. Oh, there it is. I guess I have to bump it or whatever. So now it's going down in speed. I don't know why I wouldn't before. Did you notice anything when I adjusted it? Let's see if I can adjust it again. Anything changing?
No, it's holding steady at the same angles.
Right.
That's funny.
You're getting 120 degrees, but notice the frequency has dropped. Anything else drop?
Yeah, do that again.
I'll go up again and see if you can notice anything. I guess I have to make it wake up. It doesn't want to seem to want to do it.
Hmm.
I have to force it to go back. It kind of wakes up.
Hmm.
So what's changed? Now the frequency is going up. What
The
do you
mag
notice?
the magnitude of the voltage dropped.
It did? Looks like it's increasing to me.
Never mind.
It's increasing. So as you increase the speed, you increase the magnitude of the voltage, but you still get 120 degrees. The frequency also will change as well. Your frequency will go up correspondingly. So pretty much what we're going to be doing in lab is kind of checking operation to make sure all this stuff kind of makes sense. Do we vary the speed of operation, and does that change the 120 degrees? It does not. Does it change the magnitude of the voltage? Sure does. And the reason why it changes the magnitude of the voltage is, I apologize, whiteboard would wake up. Because remember the equation we showed this in class, EA equals K times phi times omega. As I increase or decrease in the speed, it's directly proportional to the increase or decrease in voltage, right? Because this is a linear equation. So
Right.
this is going to give me a curve. As I change my speed, my terminal voltage is going to start low and then ramp up. Regardless of adjusting the field current, I'll get some nominal value of field current, and that voltage is going to increase or decrease. And it's going to increase linearly because omega is increasing linearly. The next plot we're going to look at is a different plot, but one hopefully you know really well. And it's EA times IF. What do we call EA times the EA by IF curve?
Well, the EA being the well, that's linear, so that's going to be the air gap curve.
No, it's not linear.
No, that's a curve. So if you have EA, oh my God.
Open circuit characteristic, right? Remember our test
Right.
data?
Well, I was trying to figure out if it was short circuit characteristic or open circuit characteristic. I was like, okay, well, it's got to be one of those two because it's not the
Well, you should have known the answer to that question because it's EA versus
Yeah.
IF. If it's a short circuit characteristic, you're never going to be able to measure EA, right? You can only measure IA. So you're going to develop two curves. You're going to develop a curve of EA versus IF and a curve of EA versus the actual rotational speed.
Yeah.
Okay. So trying to see if I can hit the highlights. If I've hit all the highlights, let me just double check the lab. Let's see, you got the power supply. You're gonna have to measure current. Please don't do like the lab group did today, or one of the lab groups do today, and try to measure the current by putting the meter in parallel. Not gonna work. You got to interrupt the circuit. This is a DC current. That current goes into the field. This is our mechanical prime mover that's driving our synchronous generator, and you can see we've connected the load side, or the system side, if you will. We've connected it in a neutral. So that is a neutral as specified. We've got the 4-quadrant dynamometer, turn the power on, and you're going to just go ahead and I will show you the end results. But you're going to go ahead and set the prime mover speed as indicated by the speed meter, plus equal to the nominal speed of the synchronous motor generator. Where would I get nominal speed?
That
Where do you
would
think I'd get nominal speed?
it would spec sheet.
Spec should be one spot. How about if I look right at the nameplate of the synchronous machine?
Might be a good idea.
1800 RPM. So do you remember at the beginning of our discussion, I set this as 1800 RPM? I'm going to set that at 1800 RPM. Now, I'm going to be a little bit sneaky because I'm reading it off of, move stuff over so you can see. I'm reading that point off of here, right? So let me move this to the other side. So you can see it's 1905, so I'm going to bring it down to 1800. That's all well and good, right? It's 1800 RPM and I can read it here. But how do I know if it's right? This is just some knob on some machine. or some piece of equipment, how do I know if that's actually 1800 RPM? Well, go ahead.
The frequency.
Frequency is one way, but remember, we're actually in the mechanical world. So if I look closely at this data acquisition device, can you see that the analog outputs include T and N? T is torque. What's N equal to?
RPM.
Correct. RPM. So I'm going to run my analog over to my DAC and pick that on one of the analog grounds. And I'm going to run my speed over to here where it says channel 8, which is the speed. That's just how they have it default set up. I'm going to go back to my metering window, and now I'm going to turn on this one. Excuse me. Find my speed, which is here. And you can see it says analog input 8. Click OK. And go ahead and start refreshing. And then hopefully I'm getting 1800 RPM.
Huh.
1802, which matches there. So if you want to set up your data table, right? If you wanted to have nice, easy, convenient plots, let's say I want to plot, and I'm just doing this so you have slightly different results. Let's say I want to do E1, E2, and E3 for the voltages, but then I also want to plot speed. Click yes, and now I can actually start recording my data. That's 1802. Then I can go ahead and adjust it to whatever value I want. 1854, I'm going to hit it again. And as I increase the speed, right, because I went from 1802 to 1911,
yep,
my voltages went from 102 to 106. Okay. So let's see, you can look at the oscilloscope and check those values. You can also do the phasor analyzer, but I would check with the oscilloscope just to kind of remind you how to do that. It's probably been a minute since you all have done that, but yeah, that's exactly the thing. And then the last part of the lab is monkeying with this right here, this potentiometer, and seeing what its effect is on voltage. So if I bring up my metering window and I start to manipulate this, watch what happens as I adjust it. So right now it's on minimum. The minimum here, okay, is the minimum amount of current that can be provided to it. So this is actually minimum current, maximum potentiometer, so maximum resistance. As I adjust this, look what happens to my voltages. They all go up because I'm putting more current into the machine. And if you remember, on our open circuit characteristics, you should see saturation characteristics, right? So
right,
as you push this harder and harder,
it's not going to be linear anymore.
it's not going to be linear. Yes, it's exactly right. So the only thing that I would say on this is, zoom out a little bit.
Yeah, I remember that part.
Yep. No, that's the open circuit characteristic, right? We had it on the test. So the only thing we want to do is if we want to do a plot of EA versus IF, I got to run this current, this DC current. I've got to run it over to my multimeter. So I guess I have to do this a little more. So this is going to go over here. And this is going to go over here. So now I'm going to add to my table, my data table, the ability to capture IF. So I'm going to go back in and modify it. I'm going to add on I1, I called it. But I haven't done a very good job because I connected it to I1 as shown. But I still need to make sure if this is configured correctly. So is my I1 configured correctly? Is it displaying I1?
No.
No.
Yes. Yeah. 0.618 amps.
It's close, but what type of amps are these?
AC, you got to click DC.
I click
There
DC.
you go.
Doesn't seem to matter on this one. It should,
Hmm.
but you should actually set up for DC because if you did AC in the real world, it wouldn't work. So now when I monkey with this, it goes all over the place, right? See, now it's 0.76, et cetera, et cetera, et cetera. Okay.
What's the most current that can slam through that
Let's see.
Just for funsies.
Turn it up. 0.927 amps is the maximum.
So an amp, okay,
What's the minimum?
0.
Is it 0?
No, it's not, okay,
Well, it can be because this potentiometer is not an open circuit.
okay.
But you're absolutely right, Arthur. I flip the switch and I can get 0.
Right.
So part of the lab eventually is to go ahead and actually put an external resistor so you can get a little more fidelity, because that was only 0.45 was the value that we could get to.
Right. So if you put like a, if you put like 100 ohm resistor in there, you can get a little bit more resolution.
Let's put a resistive load right here, right next to it.
Yeah.
And now instead of running over here, I'm going to run from here and here. Okay, I'm going to close this switch, but one of these resistors has to be closed before it'll actually provide current. So if you want to get the maximum current, this is not going to work really well, right? I can flip all these switches, but I'm still going to get a certain amount of resistance there. So if I wanted to get maximum current out of this thing, how do I go ahead and ignore any contributions because of this resistor?
Just unplug the banana plug and plug it on top of the one on the bottom.
Yeah, or I can also do this too, right? I can short it up, can I?
Yep.
Isn't that essentially saying the same thing that you said?
Yep.
So if I want to not include any resistance there, I can short it out. Or I can disconnect it. And how I disconnect it, I don't delete the short, I just move it off into no man's land, right? It's not going anywhere.
No.
So I actually don't have to delete it. Okay. Does your head hurt? Because we were talking about how to go through the lab for a long time. There's a lot of information, but
Probably
I'm
not
switched.
yours.
Go ahead.
I said my head probably doesn't hurt as much as yours does.
Yeah, I'm pretty stuffy. But with that being said, I'm switching it up a lab a little bit. I'm expecting you guys to do a lot more of the work by yourself. It's not a hard lab, but we have a lot of connections and a lot of things to turn. So,
No, you probably need to go hop into bed anyway.
no, I'm going to stick around during lab. I'm not
Oh, okay.
vacating. I've just been talking. So I really want you to think about what we're doing with this lab. So I'm giving you a lot of information so you can go ahead and figure it out. You basically have all the circuits right here.
Yep.
You just need to think about how this is going to work. Okay.
I kind of gave this the once over yesterday, so I've kind of,
You already got it done?
yeah,
Nice. Okay.
most of it.
Well, if you're done, you can take off. If you're not done, you can stick around and work with me, or if you feel confident, you can, or if you want to watch the video later date and time and try it, you can do that either one. So I'm going to pause the recording. And then, well, actually, let me ask if there are any questions from anybody before I pause the recording.
Hey, Paul,
Yes,
for the write-up, what are you expecting from us?
I think it's pretty clear. It asks you a lot of questions, right? So
Yeah.
I would include, and let me show you. So in my write-up, when I did it, I actually included meters, plots. I answered the questions. You know, I'll give you a sneak preview of an answer that I put. So here's my data table. I dumped it that way.
Okay.
And then plots, here's the open circuit characteristic, right?
Yeah, that's
You
from
see
Excel.
saturation. Then here's the question, briefly explained. So putting in some text like that would be a good thing.
Thank you.
Yep.
All right.
Any other questions?
No, I mean, the only questions I had was just like how to operate this stuff, which you already showed us. So that was really the only thing that I was missing, you know,
Okay.
from through this. It's like, well, this is pretty self-explanatory. It's just how to use the sim was like,
Yeah. Anybody else have questions?
No, I'm in the same boat as I just needed to know how to manipulate the sim.
Okay. Well, I'm going to pause the recording and then I will stick around and try to help people out. If you're done, have a good day. If you're not done, but you want to go ahead and try to rewatch the video to pick up parts and pause it, that's up to you. It's whatever you think is best. I'm going to stick around until the last person leaves. So you just let me know, okay? And if somebody has a good question that doesn't make sense, I can start the recording over again. So let me pause the recording.